All right. In the previous video, I showed you how to take planetary data and process it. So that means we took all of our images and we aligned it. We aligned them by clicking on the center of the planet in each one and using these centroids to align them all. And then we took the red ones and we stacked it, and we took the green ones and we stacked them, and we took the blue ones and we stacked them, making 3 separate images, a red, a green, and a blue stack. We then grouped our stacks and colored them red, green, and blue, and we had an image. In that case, in that video, we did Jupiter. We had an image of Jupiter. And I showed you how to percentile color balance. The question is, once you have a red layer, a green layer, and a blue layer in a color combo, how do you set the levels? How much red, how much green, how much blue when you do that combination? And in that video, we used a technique called percentile color balancing. And in percentile color balancing, it just assumes that the brightest thing in your image is white. It's quick, it's easy to do, but it's a pretty bold assumption because the brightest thing in your image may not be white. Now, Jupiter, which is what we did in the previous video, just so happens that the brightest part of Jupiter is white. Jupiter has all sorts of colors. It has the banded structure. It has the red spot. And the brightest thing is one of those bands, and that band happens to be white. So all the other colors are set relative to whatever percentile color balancing makes white. And since in the case of Jupiter, the brightest thing actually is white, it got all the other colors pretty close to correct. So it's a good choice for Jupiter. But not all things meet that assumption. Not all objects, the brightest object in your image may not be white. And that's the case here. Here we're looking at Neptune. Neptune, you may remember from elementary school when you'd color pictures of the planets. For Neptune, you'd always go for that blue crayon. We'll cycle back to that in just a moment. But anyway, what I've done here is I've gone through the same process. I imaged Neptune 30 times, 10 times in each filter, and I centroided and aligned and stacked and grouped and colored. And when you first color it, it kind of uses a percentile combination, which makes the brightest thing in the image, in this case, Neptune, white. And Neptune's not white. We remember from elementary school that it's blue. We'll see that it's the story's a little more subtle than that. But it's not white. So what we want to do here is not percentile color balancing, but something called photometric color balancing. And this is what we're going to use for the rest of the course, the photometric color balancing. So it's good to learn it. Now, photometric color balancing, the way it sets the levels is it uses stars in the image. In the case of the planets, all the stars are far away, so we call them background stars. Now, if I zoom out here, we can't see the stars because of how I've set the brightness and contrast, but let me just go to one of the older layers, one of the original layers, just a single frame. Here's a single frame of R, and its brightness and contrast is set differently. And you can see there's stars in the image. Here's Neptune. One of these bright spots near it is its large moon Triton. The other ones are stars, and the rest in the image are stars. Now, if you have enough stars, what we can do is use the stars to set the background level. All these stars have been cataloged, and we know they're red, green, and blue brightnesses. So we can extract them from our image, compare them to a catalog, and use that to set the levels. Now, in individual images, there may not be enough stars to do it. But the hope is in the stack, where we've beaten down the noise, we now have enough stars. Let's go back to the combination here. So the first thing we have to do is get a coordinate system on this image, because all these stars are cataloged, but we can't use the catalog information unless we know which star is which. And we know that from its coordinates. And right now, there are no coordinates on this. As I move the mouse around, watch the right ascension declination, no coordinates. Okay. So we're going to try to add coordinates. We have our stacks. They go deeper, more stars. Let's see if we can get coordinates. And I should warn you, it doesn't always work. Neptune and Uranus, they're always moving across the sky, and sometimes there are enough background stars and sometimes there's not. You have a better chance with Neptune because Neptune's fainter, so we got to do longer exposures, and that's why we see background stars. So let's see if we can put coordinates on this thing. So I'm going to go to this tab right here. It's called Show WCS Calibration. WCS means World Coordinate System. If you move your mouse around and it just says zeros, you don't have a WCS attached to your image. So I'm coming here, and I'm going to select the images to calibrate. I'm going to come down here. I don't want to select all these images that I have open, just my 3 stacks. They're at the bottom of my list here, so at the bottom of the list here. B, R, and V, I've selected them. I've set it to plate solve. If I go to an individual layer, here's the B layer. These are where the stars are. We can't see it here because I have the brightness and contrast set differently, but this is where it's finding the stars. Okay. You don't need to see them, but just in case you're curious, Afterglow is extracting these stars, and from these stars, we're going to try to match their pattern to the pattern of stars in the sky, and that tells us exactly where we're looking. Now, we know vaguely where we're looking. We told the telescope to look at a certain position. It just telescopes can't point super precisely, and so we need to plate solve. So what you do, this doesn't work if you're at the group level. There's no button here to extract a first guess. Go to one of the layers, and there's a button that appears, extract values from current viewer. So it takes this layer, I'm going to press it, and I guess I already had the numbers in there, but this image has a header, and in the header it says where we were trying to point. It says how big the pixels are approximately. Here you see a min pixel scale and a max pixel scale where we were trying to point, and this helps it plate solve. If you don't give it this stuff, it has to search the entire sky for this pattern of stars, and that can take a while. If you do this, it's going to search just around this region. It should be able to find it faster. Now I've selected all 3, and we really just need one of them to plate solve. Okay, so I'm going to hit the submit button. And that was quick. Usually takes a little bit of time, but it successfully found solutions for all 3 images. Okay, so let me close this and check. At the moment, we have a little bug. We don't see the coordinates until we hop off of an image and then back to it. But see, now it has coordinates. And if I go to the red one, it has coordinates. And if I go to the green one, it has coordinates. Okay. Now, suppose you didn't get coordinates on all of them. What you can instead do is come back here. Instead of plate solve, you can copy, and you select your reference, the one that worked. Let's say the red layer worked. And then I submit, and I'll just do it. And it just copied the red layer's WCS to the others. So again, the green has one, the red has the same one, and the blue has one. So as long as you have one, you can copy it to the others, but if you get all 3, you're good to go. Okay, so now we can photometrically color balance because it can figure out which star is which and compare it to the catalog. So let's do this. Let's go back to the display settings, the top tab. I'll go to the color combination here. And first you pick one of the 3, the red, the green, or the blue, to show the display settings. And just like we did with percentile, we're going to link the other 2 to it. That way we only have to change one set of display settings, and the others change automatically. Now, percentile, it didn't matter which you pick. With this, it doesn't really matter. There's some subtleties that can matter a little bit at the fringe. The rule of thumb is whatever your brightest thing in the image, pick its dominant color. In this case, it's Neptune. We know the dominant color is blue, so I'm going to pick that. If I was looking at Mars, I'd pick red. Okay. And now we're going to link, but we're not going to link percentile. We're going to link all layers pixel value. So I just did that. And the colors you get here now don't mean anything. These are uncalibrated colors. It came up here a little bit blue, but it's just a coincidence. If in the red frame, you had imaged a lot longer and have a lot more counts, this thing would be red. It's an uncalibrated color. Our next job is to calibrate it using those background stars. So to do that, you come down to photometric calibration here, click on it, brings up this pop-up window. You should check. Here's the red image. Make sure to put the red stack in this box, the green stack in this box, the blue stack in this box. It's pretty smart, but sometimes it gets it wrong or it doesn't select any and you have to pick them. And then we're just going to measure what are called 0 points. Press that button. What it's doing is, it's already done. It goes into every image. It extracts all the stars. It looks those stars up in catalogs, compares their relative values, and sets the level. And that's what these numbers are. These are the relative levels of the red, green, and blue layers. The correct ones, the ones that will give you natural colors if you're looking in filters that mimic the human eye, like red, green, and blue, are V and B. They're in magnitudes, but that's what they are. They're the levels. Reference layer doesn't matter here. White balance should be set to black body peaking in B. We'll explain that in a later module. Extinction, you can leave that at 0. We'll explain that in the next module. That's for if you have dust between us and your object and you want to correct for the reddening effects of that dust. There's no dust inside the solar system we have to worry about. Anyway, so you get the levels, you calibrate the colors, and you may have noticed a slight change in color there. This is the natural color of Neptune. Now, let's bring it out a little bit better. The center is a little saturated. So under display settings, when we're looking at just the planet, linear is a good stretch mode. But like we did with Jupiter, you probably want to bump the saturation level up to 100%. It's at 99.999%, but 0.001% of pixels is approximately 9 pixels, the brightest 9 pixels in the image, and they're right here. So if we bump this up to 100, they're not artificially being saturated. Oops, I did 1,000, and there we go. That there is the natural color of Neptune. And it's probably not what you were expecting. You were probably expecting something like this. This is the most famous picture of Neptune. It's taken by the Voyager 2 probe when it passed by in the late 80s. And some engineer was responsible for putting together the red, the green, and the blue, and they didn't do it carefully. And so they made this image, which is way too blue. Neptune is not actually that blue. How blue is it? It's this blue. You just demonstrated that. Of course, we don't have great resolution. It's not like we're a spacecraft passing by Neptune. We're all the way here on Earth and looking through the atmosphere, so we're not seeing any detail, but we're getting an accurate color. Now, remember to save it here, and you can extract it here to get an image. I'll do that. You can zoom in and crop it, and you see it took the pixels and then did some interpolation, making it smoother, which is kind of nice. But one last thing is let's take a look at the moons. So just like we did with Jupiter, you need to try a different stretch mode. Let's try the midtone mode. Maybe I'll go with the default preset. And let's adjust the mid-tone level percentile. I'm going to increase it. That's decrease. There's 99, 99.9, 99.99. Oh, that's too much. I'm going to back it down. 97, 98, 97, 5. Yeah, let's go with 99.97. So I got the planet here, and I have surrounding, well, one of them is the moon, Triton. The rest are stars, and we have stars throughout the image. And clearly, the stars and Triton, they're redder than Neptune. Now, let's try to figure out what's what. So for that, we're going to go to Stellarium. I'm going to turn off the ground and turn off the atmosphere, just like we did with Jupiter's moons. I'm going to come up here, make sure we are in universal time. So custom time zone. Oops, that was Pacific. UTC. Okay, and close this out. Gonna go to Neptune. There it is with Triton. And we got to get the time right. So to get the time in Afterglow, click on any of the layers. You can't do it for the group, but any of the layers. And over here, image info. And this is the start time, center time. It's about the same. I'll go with the center time. So 2024, 119, January 19th. At 0:48. Okay. Let me export this. And here's Stellarium. So it looks like we need certainly a flip. Also, let's put this in equatorial mode. That will help us line it up a little bit better. There we go. Now save it. So here we have Neptune, here we have the moon Triton, and these are just 3 random background stars. If I come back and image it the next day, Neptune and Triton will move away from these 3 stars and maybe towards other stars. And so you can add labels to your image and whatnot. But one thing to notice here is see how much redder the moon Triton is than Neptune. Triton's a pretty dark colored moon, and Neptune is bluish green, as we just determined. Okay, that's it for this video.